And so we can go over some common mistakes. So let's look at, just check your answers here. People did pretty well on this page, except for this, some people had trouble. A few people had trouble with translating to this. We didn't give credit for just, we say in terms of species and area, not log area. So if you gave your, if you still had log area in there, we didn't give you credit because some people actually had difficulty going from here to here. So we couldn't give you credit because you had to follow the directions here. And then once you do that, you can see that if you double the area, then what happens to the species number is it doesn't get doubled, it gets 2 raised to that power. If you have 2 times the area, then you have 2 raised to that power times whatever the species number was before. Okay, most people got that. Let's go on. The multiple choices where a lot of people had trouble. A lot of people had trouble on this. So, all right, this first one. This was an example from your homework where we were looking at, we saw this scatter plot that looked very, very linear, right? But then when we looked at the residual plot, there was clear curvature. See that curve here? And why was that? And that's because we changed the scale of the y. We blew it up so that you can see there's a slight curvature there, but when you can't see very well, but when we blow up that scale, the y-axis, which we could do because we're centering it at 0 now, and we're just looking at the distances above and below this, then you can see the clear curvature. And that's a very good example of why you need to look at residual plots. And because it clearly violates the assumptions, and sometimes you can't see that in the plot itself. You have to, because it's really small, the differences. But when you blow them up, you see it's a clear pattern, so we don't have a linear equation here. We can do much better. Okay, now for these, people did very well. Let's see. These people did well. Most of the rest of this, people did very well on. This was an important point that when you have binary y data, 0s and 1, the standard deviation, once you know the count, like you know the percentage of 1s and the percentage of 0s, that the mean and the standard deviation are tied together, right? So once you know the mean, you know the standard deviation, which is very different than when you have just quantitative y. So we don't need to use an F or a T because we can estimate the standard deviation directly from the data. You would never use an F or a T. That's why you never use them when you have percentage problems too. You never use F and T. Okay, so now this one, let's see what happened here. Okay, so we're given that this was actually, we're very interested in this data because we're hoping to do a randomized experiment on the experiment that you're involved in right now is not randomized. So we're seeing a lot of confounding. Even though we're getting clear differences in one direction between the online and the in-person class, we think it's due to self-selection bias. So we want to eliminate that and see what's really going on. And as you know, the only way we can see that is by a randomized experiment. So that's why we asked you on the last survey, would you volunteer to randomly be assigned to the in-person or the online section? Because we're going to try to do this next semester. So, and we wanted to see whether there would be a difference, whether there was a difference between the responses in people who are in-person and online. And it seems like in both Stat 100 and Stat 200, the online people are more reluctant to be randomly assigned. They like being in the online, they don't want to be randomly assigned. It's even clearer in Stat 100 that they want to be in the online section. So, it's a difference. So here we're trying to model this, and So we're trying to say, okay, what are the predictors of people who would volunteer to be randomly assigned? So we started with this one, and we said it's clear that the online people, because we coded it this way, that the online people are ones, and because we have a negative, excuse me, right there, a negative in front of the section, that clearly says when you have a 1 there, that means they're going to have a lower log odds, so a lower probability of being, and everybody got that. And most people got this, very good, without the chart. I was very happy. And then I even gave you the data here, so if you wanted to check your answers, you could. So some people did that to check their answers, and they saw that, yeah, this agrees, that they ended up getting a probability of 0.37 and 0.22, and they checked down here, and they got the same. All right, and then the odds ratio, you could do it this way, right? Or you could look at the ratio of the odds. We just have a binary variable. So you could have also looked at the ratio of the odds, 0.29 to 0.59. And then you can do it just directly from the data. This is very simple because we just have x and y are both equal to 0, 1 variables. All right, so if we switch the coding, lots of people got this one wrong. Why did they get it wrong? A lot of people thought they'd all change, or none of them would change. So remember what the odds ratio is. It's the change in odds as you go from x equals 0 to x equals 1. So if we switch the coding and reverse those, we're going to switch the odds. Right now, we have online over L1 odds. We'd switch it the other way. But the probabilities and odds don't change because we're not changing the probability, the volunteer coding. Look, the probability that an L1 student will say yes is not going to change. This is, or that an online student will say yes. We're not redefining what probability means here. We're not redefining it to say no. We're keeping the probability still meaning yes for volunteering. We're not changing the y variable. So there's no reason these probabilities and odds are not going to change just when we recode them. We'll just get a different expression here that will now say if online students are less likely, we'll just change the coefficient here to positive if we change the coding. Okay? And of course, then the intercept would change too. But that's not going to change the probabilities and the odds. Any questions on that? And so remember how we started? Just about I was happy that most people got this. They remember that odds is just the number of successes over the number of failures, p over 1 minus p. So they did this correctly, and then they computed the odds ratio this way, and a lot of people did check their answers. But if you left it, here I said, please leave your answers in fraction form, just to make sure that you didn't copy your answers from up here. Let's say you weren't sure what the meaning of it is, even though you knew what this was. Well, then you could have just copied these answers down here as decimals. And we didn't, some people did that, and even if you knew what you were, of course we couldn't give you credit. You probably knew what you were doing, but there's no way to tell. Okay, so you have to follow the directions. Let's look at the next one. What's the next one? Oh, this is super important. And if you get something wrong on a test, you tend to learn it better. So if you got this wrong, it's a great opportunity to learn it because it's a really important question. What does a p-value mean? And many, many, many people get this wrong. And usually it's the #1 question. If you interview for any job, they're going to ask you, what does a p-value mean? And they do not want you to say the probability that the null is true or the null is false. That's wrong. What is it? Remember, even though people misinterpret it that way all the time. So you'll get asked this question all the time when you go to a job interview if you're applying for a statistics job. I know State Farm asks it every time. What does a p-value mean? So you should know that it means, what does it mean? We're assuming that the null is true. We're assuming, we're not figuring out the probability that the null is true. we assumed that if it was true, what's the likelihood that we would get this extreme a statistic, that we'd get that extreme just like as 26. That's a hugely, if the null was true. That extreme or more extreme. So if there really was no model here, the likelihood, just by the luck of the draw, it could happen that you'd get a chi-square statistic of 26 or more when you'd expect to get one of what? 2, because it's equal to the degrees of freedom. That it could be that far off just by the luck of the draw is what? And that's the probability of, on the curve, how far out it is, that area of the curve of getting 26 or more. It's very unlikely. It's just like our justice system in some ways. It's, you assume the person's innocent. And then you say, if the person was innocent, what's the likelihood we'd see this much evidence against him or her? So that's very important to learn that. And let's see what else. Most people got all these right. You're just figuring out, let's see, where did people start having problems again? Oh, I gave extra credit here because this was actually pretty hard to get the intercept correct. So most people saw yes, it would change. The equation would change. And they got the slope. They knew that if you switch the coding, well then, you know, now that's going to change sign. So they got this, but they put the same intercept or got a different intercept. So the way to see that would be, look, we're switching when online is equal to 1. The equation at the top would give, you put a 1 in for the equation up here, you stick a 1 here, you're going to get a log odds of what? Negative 2.36 plus that. See, this comes, right? That's for the online section. Now that the online section is equal to 0, you're going to get the same log odds. You want to get the same log odds. You're fitting the same data. So now you want the intercept to be negative 2.36. And you'll get, then when this is equal to 0, for the online, you'll get the same odds and probability. So it was very, very similar to what we did with binary equations before, without log. You know, just when you had, we did this with switching the coding in regular regression. And I'd say about it, I'm not sure what % got it, but I thought it was a hard problem, so I put 1 point extra credit there. So you could get 100% and you could get this wrong, so you just get 1 extra credit point added on. So on this page, you can look at the number you got deducted, and we usually, if you got this right, it's going to be 1 less than that. If you got everything right on this page, you'll see 1 extra credit point added to your score, if you got that. In other words, if you didn't get this, nothing was taken off, but you get 1 extra credit point if you did get it. And the last one was this, and let's see, most people got this one pretty well. Some people didn't see that a 50-50 chance would line up right here. This is the probability curve, and they didn't see that they got this right, but they didn't know to put it right down here, 4. And then this scale is just the diameter, and it's equally spaced out, so you know that one's 8. And you know, I sort of chose that one because you'd already figured out the 8. You knew the probability was really small, so I thought you could kind of estimate you're on the right track there. It's 0.12. So that's the idea, and that was the exam. And it was a pretty, the average was 85. I got the average where I wanted it. I think what was happening was I was making the practice test too similar to the actual test, too similar. So I tried to change up the format a little bit, and I think that made a difference. Also, this is more mathematical, so people who are very used to log transformations and logs and stuff probably is much easier for it than people aren't as familiar, so that might have made a difference too. I'm not sure. But anyway, it's a great average and median. It's exactly where I wanted it to be. So hopefully the final will be the same way. So that's any questions on this? If you have questions on your own, just come and see me after class. Okay. So now what we're going to do is we're going to start, I'm going to go to the document camera, and we're going to start a section. This is our last section before, but by the way, don't feel bad if you did badly on this test. I mean, it was confused. Once you get kind of confused, I can really, because people ask me questions, and sometimes I could see that if you thought about it one way, it was really simple, but if you thought about it another way, it was really hard. And I don't feel bad if you got a low score on this exam. It's so easy to get confused on an exam, especially if you see questions you don't expect. So on the final, it's not going to be as, it's going to be more standard because you have the whole semester, and it's just a lot of material. So I'm going to try to make the problems easier. So don't get nervous if you did poorly on this exam for the final. All right. Now, that said, let's move on to this really fun topic on nonparametric statistics. So, what are they, anyways? Well, so far, the only nonparametric statistics we've been doing is the re-randomization test. Nonparametric statistics are ones not based on knowing the distributions or making assumptions about the distributions of the populations that you're sampling from. So parametric tests are based on assumptions that the distributions that our data are sampled from, about the distributions that our data are sampled from. Like most of the tests that we've been doing, except for those re-randomizations, assume that we're either dealing with normal populations or statistics that follow normal distributions. If, you know, that because of the central limit theorem, we have a large enough sample size that the statistics follow the, for the average, the mean, the sum of the draws, you know, of the sample, follow a normal distribution. And that's what we've been doing with all of them. Like the t-test, the f-test, they depend on the normal, underlying normal distributions, etc. And then in part 7, we saw how we could sometimes transform data with lopsided histograms into data that looked more normal by either moving up or down the power ladder. So we did these transformations to make them look more normal, and then they followed the assumptions that we were used to. But what if we can't transform the data to something more normal looking? What if we can't do that? And that happens all the time, all the time. And so we have two options. If we want to test what we've been doing for the significance test, to test what's called the strict null, that the population parameter is 0, that the difference between two or more group means is equal to 0, or a correlation coefficient is equal to 0. If we're testing that null, that the slopes are equal to 0, then what can we do? We can do two things. We can either do a re-randomization test, we did that already, and let the computer randomly sample all possible samples under the null, right? And see how likely it is to get a sample as extreme or more extreme as the one we got. That's what the p-value is. So we're letting the computers, we're assuming that the null is true, and then we're saying how likely is it that if we randomly sample from that, we'll get as extreme a statistic as the one we got. But we can also transform our lopsided data into more regular data. This is what we're going to be doing now, by replacing the values with their rankings, putting the actual numbers in order from 1 to however many, like if you have a sample size of 100, putting all the data into, just changing the actual values into numbers between 1 and 100. So we've already explored option 1, and we're now going to look at option 2. And the advantage to option 2 is that there's a few very widely used non-parametric tests that are very easily calculated and are available in most statistical software and are super easy to understand. So I think you'll like this section. All right, and so we're going to look at 3 of those non-parametric tests today that are based on ranks. There's a lot more, but these are the 3 main ones we're going to look at. The 3 main ones these are the ones we're going to look at. And they're the Wilcoxon Mann-Whitney Rank Sum test, and that's used for comparing 2 group means, so it's an alternative to the 2-sample t-test. And then there's this Crook-Wallace test, and that's if you have more than 2 group means, like 3 or more means, and that's an alternative to ANOVA. And then there's this Spearman rank order correlation coefficient for computing the correlation coefficient and its standard error. And that's an alternative to our usual R and SE, to our correlation coefficient and the standard error of R. So here, like you can see, this is on page, I laid this out for you on page 207. So you can see this is a summary of the ones we're going to be doing and the statistics we're going to be using. So today we're just going to do this one right here. Okay? So let's do that. So this is, okay, so this is what we're going to do today. So it's a substitute for the 2-sample t-test. And what we're going to do is, the idea is you have 2 groups, and you combine them into one order list from smallest to largest. So then if we had, so however many are, so you just rank them from 1 to n. And then you compute this test statistic called the rank sum, the sum of the ranks of group A. All right, let's look at this. It's much easier in an example, so let's turn the page. All right, so 2 different forms of the final. Form A and B were randomly given to a group of 15 students. 7 got the form A and 8 got form B, and here are the scores. And this comes from real-life example that we do every semester when we write finals, and we have lots of different versions to the finals. We really want to make sure that they're of equal difficulty, and so if possible, we give a group of students. Lots of times there's students who want to take it early. We have so many students. So we usually give it to a group of students early and make sure that they're not different, very different. So pretend, okay, so here, let's say we did that. So we have 7 students who randomly got assigned A, this form, and these are their scores, and 8 students who randomly got assigned this. Now, we can't do a 2-sample t-test because, why not? Because these certainly don't look normal. Look at this extreme left-hand tail, and our exam scores are really not normally distributed. They have a very long left-hand tail because it's all, so why can't we do a t? Even though we have a small, why not a t-test, a 2-sample t-test? Because look at these distributions. I mean, this distribution looks kind of like this. The 11's way down, and this is the way the final really looks. There's a lot of people who do well, but then there's scores that are very, very low down here. All right, just a few, but that's not normal. So the null hypothesis is that there's no difference in difficulty between the 2 exam forms. That's what we want. And it's even stronger than that. The means are the same. We want something that says for any segment of the population. So even if the means are the same, we don't want it to be harder for like one segment of the population. Note, this is stronger than just saying the means are the same. It's more like every percentile is the same. And that's what we want. We want the distributions to be the same. We don't want just, the mean to work out the same. So the exam forms, and the alternative is the exam forms are not the same level of difficulty for at least one segment of the population. So what I'm saying is that this has the power to detect, even if the means are the same, it has the power to detect differences in distributions. Not always, but some differences in distributions. We'll look at that later. Okay, so what do we do? So first of all, okay, so what do we do? So we combine the two groups into one ordered list rank. There's 15 altogether. And if there are any ties, we give the average of the ranks. Okay, for example, 4 and 5 both. Okay, let's look at this. So this group, 70 and 70, they got the same ranking, so how are we going to deal with that? All right, so we start with the lowest, which is 11. And we give that a ranking of 1. And then we look for the next lowest. Let's divide these into 2. We look for the next lowest, and that's here. That's a ranking of 2. This right here is going to be the highest, so that's going to be a ranking of what? You know there's 15, so what do you know? That's going to be 15. We know that already. All right, we know that lowest is going to be 1, the highest will be 15. So now this is 2, this is 3. Now these are both 4, right? Both 4. So, but we can't give them, we could give them both 4, but they occupy spaces 4 and 5, and we don't want to give one 4 and one 5. So what we do is we give them both 4.5, the average of 4, because they occupy the 4th and the 5th. So they're both 4.5. Now the next one is this one, and make sure, since 4 and 5, we already have 4 and 5 taken up. This has to be 6. So be very careful you don't give that one a 5. That's 6, right? Now 7 will be the next one, which is right here. And what comes next is 8, and this one is 9, correct? 10, 11, 12, 13, and 14, right? Okay, so those are our ranks. And now, what we do is we sum the ranks for group A and for group B. Okay, we sum the ranks and to see which one, if there's a difference. Under the null, there wouldn't be a difference. All right, so we sum these. And what do we get? When we do that, I added them all together and I got 56.5. So you choose one of the groups and add up its ranks. We did that. This is called the rank sum. You may choose either group, but it's easiest to choose the group with a smaller number of observations. So I chose this one, so that's 56.5. But if I chose this one, what would we get? Let's just do it anyway, because you really should check both of them. And this one, when I did it, I got 63.5 for that one. So now, there's a good way to check that these numbers are right, because do you know what the numbers from 1 to 15 would add up to? We can use this formula, and it says that the numbers from 1 to n add up to this. So that would be 15 times 16 over 2, which is 120. So we could check that. Does this plus this equal 120? And the answer is yes. So we know we didn't make a careless error. There's a cool story behind the guy who first discovered this when he was a kid. Gauss, Gaussian curves named after Gauss. So it's apropos. And when he was a student who didn't pay attention in class a lot because he was so far ahead of what the kids were doing. So his teacher said just to keep him occupied, sum up the numbers from, I think he was like 10 or something, sum up the numbers from 1 to 100. And Gauss just did it in his head. And the way he did it was, here, I'll show you. You probably know the story, but let's just do it with 15. He went like this. He thought, okay. He imagined 1 plus 2 plus 3. Of course, he didn't have to write them down, but he imagined that he did. So he imagined he did. And then he thought, okay, I'm going to add the first one and the last one. Right? So he added these two. We get 16, but of course he got 101 if he was going up to 100. And then he said, and look what happens. He thought of, now if I added the next two, I also get 16. He also got 101. What happens if I add the next two? We also get 16. He also got 101. And then, well, how many times? Let's just do that for half the list. So that's what he did. The formula right here is you have n plus 1 right there. That's the n plus 1. And how many times should we add that? That says n plus 1. Well, in our case, n over 2 times. It will always be n over 2 times. In our case, it's 15 over 2 times, 7.5. If you half times, if it's an even number, it would be 50 times. So he just said in his head, oh, 50 times 101. So that's 5,050. And he just said the answer. Pretty cool, huh? Isn't that pretty smart? So that's the idea, and so we should get 120 here. Because we keep doing it, and we get 12 plus 4. Here we have an odd number. Here we get 16 again, 16 again, 16 again, and then we take, right? We would have gotten, we just take, so that's why it's 7.5. If we had an even number, it would, you know. All right, so that's this. It's a cool formula. Any questions on that? All right, now we can use a z-test to test the null. Why? Because for large enough group sample sizes, and they don't have to be very large, the probability distribution for the rank sum is very close to normal when the null is true. Why would that be? Because we have, we have these uniform distributions, so they're extremely easy to figure out. The central limit theorem will kick in very, very quickly. Once we translate to numbers between 1 and 15, we have a uniform distribution, right, of numbers. And so the central limit theorem, which says that the sum of, n draws from here, like the sum of n draws from a box or the average or the will approach normality very, very quickly. The sampling distribution of the sum of the draws or the average of the draws. And that's what the more even your initial population is. And this is so even, the numbers 1 through 15, that it's extremely, the central limit theorem kicks in really quickly, as opposed to when you have such a distribution that has these really strong outliers. All right? Any questions so far? So one reason I should mention something else too. Think about when you put these numbers into ranks. Can you distinguish an 11 from a 59? Like the lowest score, wouldn't a 59, if this was a 59 in group A, wouldn't it also give a rank of 1? And the reason why why that's what I wanted is because anybody who gets an 11 on the final just is not trying at all, just writing their name basically and randomly circling things. And this person would have gotten 11 if they took group B, if they took this final or this final. They're not even looking at the questions. So I don't want him to count so much. And if I just give him because once I factor him in, if I actually took the value, then group A is going to look, this test is going to look a lot harder when it might, even if it was the same test. Whichever group this person gets randomly assigned to is going to look like the harder test because is going to really lower the average, bring it down. So I don't want that to happen. So instead, with a ranking, it's much, much better test. Even if apart from everything else, I want to rank this. Otherwise, with a small sample, it's going to give you deceptive answers. Does that make sense to people? So you have to think about what you want to do. And that's the most important thing I can say is, do you want to use this test? Do you want to use a test where you're going to you're going to lose all this information about the actual values? Do you want that or not? You're just going to have a ranking. And if that's what you want, then this is a great test. But let's say this was something that was really important. Let's say we're testing 2 drugs, and this was survival time after the drug, and somebody like dies right away. Let's say that was a 1, dies immediately after you give them the drug. That's really important information we should have, and we should leave that 1 in there. We shouldn't change it to rankings. So it just depends. It's really important to not just use a test because, hey, you followed these, you think it, because abstractly you think it might fit the data. It cares about what you care about in the data. If you want in your particular data set and what it means to you. That's the most important piece of advice I can give you in looking at problems. And that's so often lost when you take a course. So I just want you to think about that, especially with these non-parametric tests. Think about what they do and whether that's what you want. All right, in this case, we absolutely do want it. All right, so now what do we do? So now we get the expected value. How can you get the expected value? This is pretty easy because look at this part. N plus 1 over 2 is the average of the numbers. You start from 1 to n. You might think it's n over 2. That's if you started from 0, the average would be n over 2. But you're starting at 1, so it's n plus 1 over 2 is going to be the average of the numbers. This will be the average. This part is the average just of numbers of 1, 2, 3, all the way up to n. That's what we're doing here. And this part is your sample size in this group, in group A. So this is the group A sample size. So of course that makes sense. So your expected value for your summing for the ranks in A is just going to be the sample size of A, in which case it's 7, times the average, which is 8, from 1 to 15. That's what you'd expect. And the expected value for group B, for the rank sum of group B, is going to be what? You have 8 numbers, but on the average you'd expect, n times the average is the expected value of the sum of n numbers, right? So this is equal to 64. You wouldn't expect them to have the same rank sum because there's different sample sizes. So that's that. Now where does this, now the standard error you do expect to be the same, and it looks like this weird formula, where does the 12 come from, etc. Let's see what it comes out to be. It's the same for each of them. It's 7 sample size for one group times the other, times 16 over 12, and this is 8.64. And this 12 makes sense, but I'd have to explain why. I'll post a little explanation, a little proof of where the 12 comes from, because you'll see that as the standard error for the rank sum, no matter, for all of these. It will have this formula, and I'll show you where it comes from. But we'll do that. I'll post that. All right, for now, let me just tell you, this will definitely be given. You don't have to memorize this. This is given on the final. Okay? So you'll have this on your cover sheet, cover of your final. So now we can calculate the z-score. All right, so we'll calculate, we could look at exact probability tables for this, and we'll look at that later. But they're usually in terms of something called the Ustatistic, which we have to do on the next page. So for now, let's just do the z. Let's just assume it's close enough to a z, to normality. All right, so we're just going to do our usual thing. Observed, what did we observe for the rank sum? We observed for A, let's do it for A, we observed 56.5. What did we expect under the null? 56. and the standard error is 8.64. So we get this tiny little z-stat, which is 0.058, right? So of course it's not going to be significant. It's so close to 0. We're going to get a huge p-value. So here's what it will look like. As a z, we have 0, 1, 2, 3. And we got this tiny, tiny, so hard to even draw. What is this? This is z is equal to 0.058. And here on this side, it's z equals negative 0.058. And we're just trying to find the area in between those so we can get the p-value. So what's the middle area there? It's just a tiny little slice. And let's just say it's 4%. I mean, it's certainly not significant. Let's just say 4% here. So our p-value is going to be what? We didn't specify which group was going to be better, so it's going to be two-sided. So it's the probability that we'd get this extreme, a z-stat, when the null is true, is almost 100%. So we can certainly, I'd be so happy in this case because I'd say this really means the two exams are of equal difficulty. So, all right, so mark Z, okay, calculate P. The P is just what? P is 100% minus 4%. So we have a 96%. That's about as big as we've ever seen. All right, now, just to make it more clear what we're doing, we always do the other axes. So let's look at the rank as a rank sum. Right in the middle, we'd expect for A, we expect 56. That lines up with 0. That says 56. Sorry, you can't even see it. But this right here is where that's what we expect. And what did we observe? 56.5. That's what it is. And we're trying to say how probable that is. Now let's see, so what do? We reject the null. And I'd be very happy. I mean, we cannot reject the null. Oh, do not reject the null. We cannot reject the null. The null was that the two exams are the same. We cannot reject the null, and we conclude what? That the two exams are the two forms of the exam of the final are of equal difficulty, and that's just what I wanted. This is a case where I wanted them to be as close as possible. All right, whereas if I'd done it any other way, this one would have looked like it was much harder because of the 11. Now, compare ZB. What if I'd done ZB instead? What do you think? What would I have done? What would the z-score for ZB be? So for ZB, you can probably guess the z-score would be what? We observed 63.5 right there, and we did expect what? 64. And we have the same standard error. So do you see how we just get the same z-score? You get a 0.5. This is a negative 0.5 in the numerator. Here was a positive 0.5 in the numerator. So we get negative 0.058. So this right here would be, let's draw a new axis. If we did RB, we'd have 64 in the middle. And here's where this little thing right here is 63.5. All right, So the idea is what? They're just, ZB is just going to have the opposite sign of ZA. So they'll have the same p-values. Even if you did a one-sided test, because if you said ZB was bigger, that would mean ZA is smaller, and vice versa. So they'll give you the same p-values. So that's the idea. Any questions on it? All right. Now, as I said, a lot of people, even with sample sizes 6, use an exact probability table. I'll show you those, but they're not in terms of rank sums. They're in terms of something called Ustatistics. So often people like to do rank sums and then convert them to Ustatistics because there's an easy conversion, or you can, they're really the same statistic. They use Ustatistics just because they're smaller numbers. I think that they're easier to calculate from the get-go. So let's just look at how to calculate a U-statistic. And some of you who've looked at things like, I don't know if you ever studied ROC curves, but the U-statistic features prominently in those. So you might have seen this already. But a variation on the rank sum test is to use the U-statistic instead of the rank sum statistic. And the U-statistic sums the number of times group A scores surpass group B scores. And UB is the number of times group B scores surpass group A. All right, so let's just do the same example. You'll see how to do it using a U-statistic, and you can see which one you like better. They both will give you the same results, the same z-scores. Okay, so let's do this. So now, so we're looking at group A scores, and we're seeing how many times each one of these surpasses group B scores. So, for example, you look at 11 here, and 11 is smaller than every single one of those. So it would get a score of 0, a U count of 0. The way I think about it is if, like, imagine these are two teams, and they're all playing like singles matches against each other. So this group has 7 members, and each one of these members, each one of these 7 will play a match against all 8 of the other team on the other team. And so you're just, and then so you're giving, so this person didn't beat anybody. He contributed 0 to his team. So then you look at the next one, 70. How many matches did he win on this team? You can think of, well, he beat this one, and this one is 2. And then he tied for this person. So we count ties as a half. So this person has a U count of 2.5. Now we can go to 75. And what's his U count? How many did he beat? 60, 65, and 70, so it's 3. Does this make sense? Do you want to take a minute to see if you can fill in the rest and then see if it agrees? Okay, so 85 beats 1, 2, 3, 4, 5, so that's 5. 88 also beats the same 5. And 92 beats 1, 2, 3, 4, 5, 6. And 96 beats everybody, 7. Everybody except this guy, so that's 7. All right, so now what we do is then we choose one of the groups and add up its U counts. So we'll do the same thing. And add all those up, and I got a 28.5. All right? So that is the U count here. Now let's just do the same thing with the other one. Make sure that you know how to do this. So let's just divide these. Okay, why don't you start it off? Just get the first two numbers, or the first three numbers. Okay, 60 just beats 11. So just beat one person, counts 1. 65, just same, just beats 11, so he only got 1 point for the team. 70 beats 11 and is tied. So 1 for beating 11 and a half for being tied, so that's 1.5. 79 beats 3 people, so he gets a score of 3. 81 also just beats those same 3 people. 90 beats 5 people, right? 1, 2, 3, 4, 5 scores. 95 beats 6, and 100 beats all 7. Isn't that right? Is that what you got? Okay, so now we add them all up. And we get 27.5. All right, that's here. Now, you can do the same thing. These two have to add up to what? They have to add up to NA times NB. Why? 7 times 8. Do they? Yes. So that checks. Why? Because think how many total matches there are. Because this is equal to 7 times 8, which is equal to 56. Because there are 56 pairwise comparisons. Each person, each of these 7 people, or each of these 7 numbers, I keep thinking of tennis matches, each of these 7 numbers plays each of these 8. So it's 7 times 8. 7 times 8 matches. Okay? So you can think of 7 times 8 singles matches in tennis. All right? So that's 7 times 8 pairwise comparisons. And so you can check they add up. All right. And now we can do this. Now, what do you think the expected value would be for them? Well, what the formula right here, let's look at it. It says the expected value for both groups are going to be the same, no matter, even if they have different sample sizes. For both groups, UAs, and it's going to be what? 7 times 8, because there's 56 matches, and you'd expect half to go to one team and half to go to the other if they were randomly divided, if there was no difference in abilities between the two groups, or no difference in, if it was really no difference in difficulty between the two exam forms. So that would be 28 for both of them. You can see that because there's going to play, even if there was one person here and 8 people there, this would be, there would be 8 possible scores that person could get. You'd expect them, if they're right in the middle, to get 4 because they play 8 matches. So it doesn't, every single match has has a player has a number from here and a number from here. So it doesn't matter how many people are on this team and how many are that. You'd expect half of them, if they're equal difficulty, have to go to one and half to go to the other, right? Because you can't have a match without one number from here and one number from there. Does that make sense that the sample size doesn't matter for this? Okay. So that's what this is. And this is exactly the same standard error. Now, this shouldn't surprise you either, that the same, because UA and RA are just differ by a constant. They just differ by a constant. And So the standard error is just this. If two groups of numbers differ by a constant, then that's not going to affect the spread. It's just going to be a shift. And the reason they just differ by a constant is, think about this. If group A had all the lowest numbers, like the 7 out of the 15 lowest numbers, its rank score would be, its UA would be 0, and its rank would be just the 7 lowest numbers added together. Maybe to, in other words, UA, which is what? Right here, the UA is 28.5 plus n times n plus 1. And it's, what's that, 7 times 8 over 2 should equal what we got before, 56.5. Right there. And it does. They just differ by a constant, so they have the same standard errors. All right, now, and they're going to have the same z-scores. I bet you can see that pretty easily. So let's try it. So we got an observed of 28.5 minus 28. You can see it right away. They just have the same numerator of 0.5, and it's over the same standard error. So we get 0.058. And if we did it, we'll just, here we have this 0 as a z-score. And now the u's have the same expected value, so we can mark both of them as 28 here. And here we either got 0.5 above or 0.5 below. So we get either right here, this is UA equal to 28.5, right? That's UA. And as a z-score, it's going to be equal to 0.058. And here, what do you think we'll get? ZB is going to be what? We have 27.5 minus the same expected value, 28, right in the middle. That's the 0.5 in this direction, but you have to get the z-score, we have to divide it by its standard error, and we get a negative 0.058 on this side. So here we get z equals negative 0.058, and here that was what UB is. And that's UB. That was equal to 27.5. And then we have the same exact everything. All right? So that's pretty much, say 4 in the middle. And it's the same thing. 100% minus 4%. So we get 96%. And we cannot reject null. The two exams are similar. They yield the same, this is the important thing. All right. They yield the same exact thing. Before we go on, maybe we should just make sure, let's just do an iClicker, make sure you know how to do some of this. So let's go here. 8 numbers are randomly divided into 2 groups of 4 each. What's the highest possible rank sum a group could have? What? Yeah, that's the whole point. They can be any 8 numbers. What's the highest possible rank sum? I should have put other numbers too. the best thing about making a mistake. Then you start doubting me and start being critical. It's good. No, it's good. It gets you to think for yourself. That's the best thing a teacher can do, really. I didn't do that on purpose, but the best thing is to have people say, hey, wait a minute. Maybe I know something more. Because you probably do in lots of cases. In all your classes. Okay, so you all done with that one? Let's just stop it. And what did you say? Yeah, the answer should be 26, right? Let's see, people... Yeah, because you have set the highest. If you rank them from 1 to 8, you have 1, 2, 3, 4, and then what's left is 5, 6, 7, and 8, which sums to 26. Okay, great. Does that make sense to everyone? What would be the highest U? Let's do that. The highest U, and I'll put the numbers. What do you think the highest U would be? We can do that. You think about it, and I'll tell you what numbers to think about. You probably can figure it out on your own. But what 4 groups, what do you think the number, what would be the highest? It would be, so let me just, would it be, okay, so pretend the numbers are 10 is A, 16 is B, 22, let's just leave these same numbers. What's the highest U statistic? We're leaving these same numbers. Okay, let's see what you think. I'm going to stop it. Did everybody get a chance to vote? Which one of these do you think it would be? All right, let's stop it. The answer would be, let's see, 16. Great, because each one would beat all 4 of the, outscore all 4 of the other numbers. So it would be 4 plus 4 plus 4 plus 4. And as we said before, that you know, you can translate, this is a good example where you could translate from a rank sum into a U-stat by just subtracting off 26 minus the first 4 numbers added to 10, so 26 minus 10 is 16. By subtracting off the lowest group. All right, so that's pretty good. Let's go back to our document camera. All right, and now, that's what I said here. So, all right, so now, for small samples, the normal curve's not such a good approximation, so you can use these exact probability distributions. And these tables are always in terms of U and not in terms of rank sum. So, but that's not a problem because you can convert data to ranks or U counts. So these tables show the exact probability distribution of the U stat. And the tables below give the critical value at p equals 0.05, so that's alpha equals 0. So this is the critical value, so this is U critical at alpha equals 0.05 for the smaller U stat. And that's the way I've always seen them. This is what they look like. And so now we want to compare. We know that it's not significant, but let's say we wanted to use a table. We already got a p-value of what? It was crazy, of 96%. We don't have to do this. But let's say you wanted to do this. It's just an example of how we would do this. we know we're not going to get significance. So what does this say? So you have these two numbers. This is right here, is the sample size for the smaller group, right here. And here's the sample size for the larger group, right here. Here our smaller group, and 1 is 7. So this is sample size of smaller group. You know, they could be just the same. And this right here, and 2 is sample size of a larger group. And our larger group was 8. So we're looking right here. And that is our U. That's the critical value. We want one as extreme or more extreme. That's even smaller. This is the small one. If we'd been looking at the big one, we'd want as extreme or even bigger. So if our Ustat was smaller than this, then we would reject the null. And our Ustat, what's this if it was smaller than that for the smaller one? So our smaller Ustat is what? $27.5, right? Wasn't it 27.5? Yeah, it was 27.5. Our smaller Ustat is equal to 27.5. So we know we're not going to, it's not, you know, it's not even close. So, and so it is. Now, what if it was divided up? What would our Ustat for the little one be if the 7 lowest numbers were on team A? If the 7 lowest numbers were on team A, we'd get a Ustat of 0. And we would reject, right? We would reject. What if we had one person who beat everybody on the other team? So we beat all 8 on the other team, but everybody else was 0. Didn't beat anybody. We'd still reject. Okay? Do you understand how to do this? Now, so what do I say here? Rearrange the exam scores to find the Ustat closest to the critical value without going on over. Well, I just gave you examples. This is just for fun. So you can just try it on your own. Just try different combinations and see which ones you'd reject the null on. All right, now let's see what else. I think you've had enough for today. I can tell that it's going to get, it's simple, but it's a lot to process. So the homework's up, and I think you just do best to just do the homework, and you'll learn it best, right, if you do that, rather than me going on. Now, if you have a question on your own exam, come up in